Thank you for having me. I haven't been at the University of Bonn in 30 years. I came here my first year. I was a professor in maybe 1990, and there were 3 graduate students at my presentation. So I feel like I'm making progress. So that's a good thing. I am going to talk to you about a research project called the Data Intensive Farm Management Project, which is DIFM. And this project is something that my brother and I thought about more than 20 years ago. And I was being a human being and raising children and everything. And when my kids finally kind of got out of the house, I decided that, you know, I would really pursue this harder. And so that's what I've been doing for the last 7 or 8 years, and just having a great time. And I'm excited to talk to you about this project. I'm not going to present to you scientific findings or statistical findings. There's a lot of research going on within this project where that's a real possibility. Really here, I want to talk about the project and publicize the project because, well, you'll see why I want to do that soon. We have been funded by 2 different grants, $4 million grants from the United States Department of Agriculture. So that's what's that's where the money's coming from. Okay. In the current project, what we wrote in the proposal was that our multidisciplinary team was going to work on a large set of diverse farms and with farmers to create a super efficient, principally automated system for on-farm experimentation, precision experimentation, the analysis of the data generated, and the practical application of that analysis to enable farmers to make data-informed input management decisions that improve both the economic and ecological sustainability of crop production. So I'll talk about how we're trying to do that here. As you know, here at PhenoRob, there's a great deal of talk about agriculture big data. It has been. That's been the huge buzzword around the agricultural research world for many years now. Big data, big data, big data, big data. And I want to pull back a second and think, because a lot of garbage is a lot of garbage. So the question is, what is the data we need? What kind of data makes sense? Et cetera. And so I want to think about, from an economist point of view, what kind of data we need. So I'm going to try to break this down conceptually. Without being too obnoxious at the same time. So if you think about yield, any kind of crop yield, I think yield can be thought of as depending on, given the genetic makeup of the plant, let's put it that way. Given the genetic makeup of the plant, yield depends on managed inputs, like what rate of nitrogen you put on the field, what date you put the nitrogen on the field, what seed rate you use, et cetera, et cetera. So that I'm going to call X, what people do on farms, choices people make. Spatially dependent characteristics, C. So the siltiness of the soil and the topography, the slope of the soil, all these things that just kind of come, that are spatially variant within a field, but are not controlled really by human beings, at least in any kind of short run. And third, basically weather, unmanaged time-dependent variables. So I think that pretty much covers it. It's hard to think of anything else in my mind that yield depends on. And so let's call that F the God function. People have been trying to figure out the God function for centuries. There have been, I have a paper published in 1784, where somebody was trying to think about, was running agricultural experiments to try to think about this function for wheat, somebody in England. So people have been trying to think about what this is forever. And principally the way we've gotten data, agricultural scientists have gotten data to think about this function is through small plot experimentation. So I'm sure many of you are familiar with small plot experimentation. It's very useful, it's very important, and it will continue to be very important, you know, for centuries to come, but it's limited. So a small plot experiment is often on a piece of ground the size of this room, or maybe twice this big. And it has small plots, maybe the size of this table or bigger. And on this plot, you might put down 80,000 seed per hectare. And on this plot next to it, you might put down 100,000 seed per hectare or whatever. Later, you come by and you pick up the yield and you try to get data that's going to be useful to estimate this function. And that's great. We learn a lot. But the problem is, in such a small area, the characteristics of the field don't change very much. It's often pretty homogeneous in such a small area. And so that limits what we call, statisticians call the infraspace of what you learn. You can find out about how wheat responds to nitrogen on this part of ground in the world, but that may not be how wheat responds to nitrogen across the road, let alone across the ocean. Okay. Getting different weather observations, of course, takes time. So people run experiments over several years, and there's a lot of small plot experiments out there that have gone on for 20, 30 years, and then that's a good thing. But the size of small plot experiments makes the inference space, makes this small, and that's a problem. And so the question is, what do we do about it? Or why? Why do people do small plot experiments? Well, as an economist, I would look at that and say, because it's expensive. Why is it expensive? Because you need graduate students. Graduate students need to be out there in the rain, having the professor yell at them, left, with measuring sticks, you know, measuring. And graduate students, as you know, make too much money. And so it's very expensive to run these experiments. And so what would be great is if we could figure out a cheaper way to run these trials. And that's what we're trying to do. We're trying to take advantage of new technologies to run much cheaper experiments so that we can get the kind of data that we need to learn more about this function. And once we know more about that function, we can help farmers farm more efficiently, which has both financial benefits and environmental benefits. So if they've made you take an agricultural economics class or an economics class, then probably in the first month, you saw this picture, which is this F here. That's the God function. And here I'm just going to, it's also called a yield response function, also called a production function. And it's just a function representing how yield depends on, say, nitrogen rate. Okay. We generally think that yields rise with nitrogen rate and then flatten out. Okay, especially for corn, for maize. So great. And the question is, great. Once you know that, what do you do? Well, an economist could show you in a few seconds with some calculus, or if you were an 18-year-old, would show you in 45 minutes in a lecture why the economically optimal input application rate is where the slope of the function is equal to the ratio of the input price to the output price. And I won't go into detail, but it's not too hard of a concept. All right, so what's this tell us? It also tells us, of course, that the profit maximizing quantity production is not the maximum amount of production, right? You don't want to maximize yields if you want to maximize profits. Those are two different things. All right. So this tells us that to know the optimal input application rates, you need to know two things. You need to know prices, and you need to know this yield response function. And if you know those, then you take off from there, which is why people have been trying to figure out this function for centuries. All right. And a key point I want to make here that I think is missed in a whole lot of the common talk about agricultural big data is that if you don't know, if you don't vary manage input application rates, then you don't know how to map field characteristics and then determine optimal rates. You have seen, if you've looked on the internet at all, people flying drones and robots and satellites and electroconductivity machines over fields and taking pictures, right? And they say, oh, we have 39,000 terabytes of pictures from outer space. Now what? Well, I would maintain to you that if you don't vary management variables, that those pictures from outer space don't tell you very much about what you need to do. Because the whole question is, how do we manage the management variables? And if you don't change those to see how yield responds to different management strategies, then you're not going to learn anything about how to change your management strategies with your data. So here's an example. Let's say we have a field that has a sandy part and a silty part. And sure, the silty part probably gets higher yields than the sandy part in most years. Okay. And so we would like to know, okay, what are in these different parts of the field, what are the responses, right? What are the response functions? And for the same reason that I showed you in the previous diagram, you know, we want to know what that curve looks like, but it's different in different places. So if we want to manage any input site specifically, okay, we've got to know how this response function changes over space. All right. Well, if our data looks like this, we can't fit a curve through a column of data. And so if all we do is take pictures from the sky and then allow farmers to do what they do, which is pretty much everybody in an area will do more or less the same thing, then our data is going to look like this. And we can't figure out what those yield response functions look like. And so what we end up with is a lot of data from the sky. What we're trying to do, and what people have been trying to do for centuries, is vary nitrogen or seed rates in experiments and then fit those curves. And that's a very simple diagram of what people have been trying to do for a very, very long time. But in some sense, those advocating agricultural big data have forgotten that they need to do this if they want to do much with their big data. All right. So the more we know about this function, F, X, C, and Z, the better we can help farmers manage their input applications. On-Farm Precision Experimentation, OFPE, is revolutionizing how data can be generated for the estimation of this function. So what's OFPE? Here is an on-farm precision experiment. Okay, this is bigger than this room. Okay, this is basically 3.7 kilometers by 1.7 kilometers. And this was a field trial that we ran in the state of South Dakota in the United States in 2020. And you can see there's thousands and thousands of observations with different nitrogen rates on that field. Every one of these little squares is about 18 meters by 70 meters. Okay. And we have used, there's a person planting one of the trials. That's not the South Dakota trial. But up there is just somebody driving his tractor, and we're making the experiment go into the ground while he just drives. Okay. And as a result, we get this kind of data. All right. Now this is, of course, there's a lot of noise in that data because this diagram doesn't show different field characteristics and different weather, et cetera, but still you can see the kind of data that we're getting. So that's, I think, it's over 1,000 hectares, that experiment size. All right. How do we do this? Well, we take, the farmers send us, at least in our part of the world, the farmers have tractors. All the tractors, all the equipment comes with precision technology. When they buy it, it's just there. And sometimes they use it and sometimes they don't. Okay, but they have the ability, they're hooked up to GPS. They have the ability to vary their input application rates over space by following basically a computer program, which is a shapefile. Well, what we've done is we've taken this technology and we've written computer programs that design various kinds of randomized trials, okay, and then we suck those up into the farmer's laptop or whatever, into his equipment on his tractor, and then the farmer just drives. So that's what makes this so expensive, is that it's not very hard for the farmer to do this. They've all played with this equipment before for a number of years, and they get it. So what I want to show you here, if I can, hopefully this will work. This is a farmer in Illinois, and he's driving and taking a picture of his monitor with his iPhone, and you'll see this bounce up and down. This says 29.65, which means that his machine is trying to put down 30,000 seed per acre, and it's not quite off, but it knows how much off it is. Okay, so basically this is going to bounce around 29.89, 29.40, etc., and then all of a sudden, boom, it's going up to 40. Okay, and it takes just a second. It's at 38 per second, then it's up around 40. Okay, so this person is able, without grad students, without being in the rain, without measuring tapes, et cetera, able to put this huge experiment in the ground and really not doing anything different than what he's usually doing. The tractor steers itself. He can take out his iPhone and he can take a movie of what he's doing while he's doing it. So my brother, the crop scientist, figured this out in the 1990s. It was obvious to him. He said, we can use precision technology not to farm precisely, but to get information. Smart guy. He's really hard to get along with. Smart guy. All right. So this is, if you can listen to this, I hope you can hear it. One of our farmers, then what we do is we have the combine, the harvester runs a machine, and it will run up and down these strips, and then it will register the yield. It will measure and register the yield. So this is one of our farmers who enjoyed this, and so he put this up on the internet. So see if you can hear this. Uh-oh. You can't hear it. Anyway, he ends this by saying, isn't technology great? Okay. So that's an actual picture, of his. It's not a picture. It's a GPS related presentation of his monitor going up a particular plot that had a particular seed rate, and it's harvesting. So here's the data from what you would usually get from a farm that uses the same seed rate across the whole farm. And most farmers in the Corn Belt United States, they don't try very hard to vary their seed rates over space because they don't know how. They don't know how to. When precision technology first came out, it was full of pictures of beautiful yield maps, and they're very colorful, and they would have diagrams with satellites. And it took the farmers about 2 years to figure out, okay, but how do I do that? And since then they figured out, we don't really know where to put how much seed. So I'm going to do this. I'm going to put the same amount everywhere. And then the data ends up looking like this. This is seed rate. This is yield. Whereas if you can see here, this is an actual as applied map. And it shows, if you can see, sometimes there's dark green, sometimes there's light green. That's the actual data that was applied. So, this works. This actually works. And here's the data we get after seed rate and yield after we harvest the data. So it gives us a new kind of data, and I think an exciting kind of data. And from there, we can do a lot of things to search for and present optimal seed rate maps, say, or optimal nitrogen rate maps. Now, I hope that you have a lot of questions because you realize it's much more complicated than this. But still, I'm trying to show you the basics of what we're trying to do. Okay. We are trying to create a cyber infrastructure to scale up on-farm precision experimentation research. And right now, this year, we're doing about 100 trials. And we're doing them in, I think, 15 United States in the United States, and we're doing them in South Africa, and we're doing them in Brazil, and it looks like we'll be doing some in Canada this spring. Okay. So that's great. But we don't want to do 100 a year. We want the world to be doing 10,000 per year. Our vision, our hope, what we said we'd try to do was make it possible for farmers all over the industrialized world to be running experiments on their own farms on a regular basis. Maybe not every field and every year, but still on a regular basis and using this technology to gather information, to analyze the data, and to make data-intensive decisions. Now, for us to do that, of course, is a huge challenge because to scale things up to this level is something. We can't have a PhD graduate student. We can't assign one to every farmer, right? So they can spend and write a chapter of their dissertation on every experiment. We need to automate things enough so that this can all happen on a scaled-up basis. So that's what we're trying to do. How are we doing? So this is a very busy diagram that kind of shows the whole cyber infrastructure. I'll try to go through that sort of one step at a time. The first thing we're doing is we're building a user interface, a front-end portal. And with that front-end portal, and we have a beta version of this now, address, and you can play with it yourself and design some field trials. The idea is that a farmer would sit down with a consultant, and all over the world, I'm sure in Germany, there are agricultural consultants, and farmers go to them and say, can you help me decide, when should I plant? How much seed should I put down and where, et cetera, et cetera. So there's a whole profession out there. And our vision is to give the consultants a few days training and make the software easy enough to use that the farmer and the consultant can design one of these trials and gather the data. A lot of the data now, you don't have to use flash drive. It just goes straight to a computer from the tractor these days. So everything can be wireless. And so you bring in the computer signal from a computer someplace. It comes to your tractor. The farmer drives, it puts the trial into the ground. And then come yield time, the farmer drives, and that data goes back to the computer in wherever it is, Bangladesh or something. And so you have this raw field trial data pretty easily. Okay, it's quite doable. Okay, so that's how we want to get one kind of data. Second kind of data is all sorts of spatial data. And so this is where data from remote sensing, data from field robots, okay, data from soil sensing, data from proximal sensor, that is an electroconductivity sensor, a various electroconductivity sensor. That data also comes into the raw data set along with weather data. Okay. And then from there, the data has to be processed. Now there would be a whole different talk to talk about how we process this data. But whenever you get this kind of spatial data, there are things that are wrong with it. The farmer stopped and smoked a cigarette when he shouldn't have, or something. And when you look at it, when a human being looks at it, you can say, uh-oh, something's wrong here. And you can adjust that data or take the data out. But we can't do that with many thousands here. And so we're designing algorithms that will process it. Once that data is processed, we are putting it into automated analytical engine. What's that automated analytical engine do? Well, this is the chief challenge. of what we need to be doing over the next 3 years. So we've gathered a bunch of different scientists, some computer scientists who do artificial intelligence and machine learning. Of course, we have some economists. We have some statisticians, and we have crop modelers. And we're trying to organize ourselves so that we can work on creating an engine that can take in data that's been processed and analyze it more or less automatedly and come out with better and better designs for farmers to run experiments and to manage their fields. And with that, we're trying to close the loop of this infrastructure with, again, the front end, where the consultant can sit down with the farmer and use the data and use the analysis to make better decisions. We don't want to just give the farmer a map and say, do this. They don't like that. They want to be able to make decisions. We want to create a tool that the farmer and the consultant can sit down with and use their agronomic intuition to think of that. And we want that to be an interactive tool where they can put in what if situations. What if it had rained more in June? How would this have changed? What if the price of wheat had been higher? How would that change the situation? Okay. So we're trying to create, and we're in the first year of 3 years of work on this. We're trying to create something that is a decision tool that is truly based on data mostly from the farmer's own fields, and can help these people do what they do, but give them real information from real data from their own farms. So that's the goal. I hope in 2 years I can come back and say how well this is working. My suspicion, my hope is that in 30 years, my graduate students are still working on this, because this is a huge challenge. But I hope that it's really makes a difference. I think there's so much more data than there used to be, and I think with this on-farm precision experimentation, we can get so much more quality data that it's worth it to try to do this. All right. So I see this as a very long run challenge. All right. We are also creating with the CyberInfrastructure an outreach or an extension program. And what this is supposed to do is help crop consultants around the world learn how to use this software and learn how to do this system, and to help farmers as well, and just have a basic communication platform where people are discussing this kind of thing together all the time, with training videos, with people complaining, places where you can complain about the people who invented this, et cetera, et cetera. All right. We are working with the Oracle Corporation. They've been generous to us. We want the data to be someplace where ransomware people can't get at it, right? This data is owned by farmers. So it will be owned by the farmers upon whose land these experiments will run. If you're a crop consultant, the farmer will give you permission to deal with the data. And maybe if you've got 50 farmer clients, you have a whole place that you can go within the infrastructure to look at your various farmers, what trials they're doing, what the reports are, et cetera, et cetera. That's our view. This will not be, I didn't make this clear at one time or another, but this is not something where my group gets a lot of data. That's not the point. We are going to provide, the point of us is to provide a very efficient infrastructure where data can come in, where people can get at their own data, but it's very safe and protected. The point is not for me to having access to this data, or for me to have any right to this data. If you're a researcher and you run these kind of trials, you work with your farmers, and it's your data. I personally will have no access to it. Somebody somewhere will have access to it, of course, somebody in the Oracle Corporation or something, but no legal access to it. Okay. So what I'm trying to say here, we're not doing this to get other people's data. We're doing this because, you know, it's supposed to be, we want this to be something that happens in the world, and we want this to be something that goes out into the private sector. Just trying to create infrastructure that people can use that for. Not farmers own the data. Oracle-based system will provide easy access to efficient data. By contract, only those who generate the data have access to the data. The item has no right to the data, and foreign management. These are some of the people involved in various parts of the United States. You can see there's, I don't know, 30 or something various professors and a bunch of graduate students. And so we are doing research in the far north, in the far south, on wheat, on corn, on cotton, on barley, on soybeans. So that's a lot of fun. We're working with some people in Argentina at the National University of Córdoba. We're working with a group in South Africa at the Bureau for Agricultural Policy Analysis. And they are running actually 10 trials this year. It's been really fun working with them. I'm hoping to hear from some people up in Canada that are enthusiastic about it. Hopefully. So we're trying to make this an international thing. We're already making this an international thing, but we don't have anything going on in Europe. So that's kind of why I'm here, just to publicize what we're doing. I have some contacts with a place called the European Union Center at the University of Illinois, and their job is to encourage University of Illinois research collaboration with the EU. And so there are some resources there, and they're currently writing some grants that if I find the right kind of cooperation in the EU, that I can go on to that, and et cetera, et cetera. So there's a lot of institutional support for what we're trying to do. And when Thomas Heckeley invited me here, he was just going to have me give a Zoom presentation, but I was going to be in France anyway at an On-Farm Experimentation Center. So I'm not the only one talking about this. There's a tremendous amount of talk all of a sudden about on-farm experimentation, part of which is what we're doing. And so I'm very enthusiastic that this is something that's going to continue to happen in the future. Anyway, I'm going to speak with some people in Eastern Germany where they have bigger farms tomorrow to encourage this with them. Obviously, if it's only a 40-hectare field and the farmer has one field, then it's not as likely that we're going to be able to use this technique as if they're larger fields. Okay, if you are at all interested in any of this, just let me know. Just send me an email. I'm happy to talk with you. We are getting so much data that every once in a while, in the right circumstances, if people just want to analyze data, we're ready to bring people on board to write papers, et cetera, because we're trying to get research out, but we're trying to do 5,000 things at once. And so there's also just room for people who are statisticians and et cetera, who want to work with this kind of data. So let me know if you're interested in that. I am trying to get together money to make for a big international conference next year in January in Miami, Florida, for obvious reasons in January. We don't want to do it in Illinois. And so please keep your eye out on that if you continue to be interested in this kind of thing, et cetera. Yes, any questions?